well, this one's easy because you can just put whole numbers of coefficients to keep it that way. And again, we got this heat of formation from that appendix. Okay, so let's talk about calculating standard enthalpy change for a reaction. So any reaction can be written as the sum of formation reactions or the reverse formation reactions for the reactants and products. The delta H for the reaction is the sum of the heat of formation for the component product. So delta H of the reaction is equal to the sum, so that kind of weird symbol means sum, of the heat of formations of the component reactions. So products plus the sum of the reactants. So this weird symbol means sum, and then N in this case means a coefficient of the reaction. Remember, N stands for moles, and the coefficient is telling you the number of moles. So here we have carbon and hydrogen forming methane, and then we have carbon and oxygen forming carbon dioxide, hydrogen and oxygen forming water. So there are 3 different reactions. Now notice that the heats of formation are all negative because that means they're all exothermic reactions. And so what happens is, in order to form this equation, you remember you got to go back and flip some of the reactions and cancel out the different ones that appear on both sides in order to get the correct product. So, and the next slide it does that. So next slide, it flips the reaction. So if you notice on here, it was carbon plus hydrogen gives us methane. Well, we have to flip it because methane is on the reactant side. Then when you do that, you got to flip the sign. The next one is we want oxygen on the reactant side. And so we can keep this one the same. And then we can keep the hydrogen plus oxygen the same also. Now, what happens is they cancel out the carbons. So the carbons cancel out because they're on both sides. Hydrogens cancel out. And you're left with oxygen. So you're left with 2 oxygens. So there's 1 methane, 2 oxygen. That's what we want. Yields carbon dioxide and 2 waters. Okay. Now notice that there is only 1 water here, but we ended up with 2. So it says that delta H, or the heat of formation, equals the negative 393.5. That is the delta H of the methane. Okay, and again, we looked that up in the chart. And then here, there's a 2 oxygens, delta H of oxygen, minus, because that's our, if you look back at our formula, it's going to be a minus sign, minus the delta H for carbon dioxide and the delta H for water. And so that gives us negative 802.5 kilojoules. Okay, so yeah. All right, so let's look at this example. It says use the standard states, use the standard enthalpies of formation to determine the heat for the reaction. So we have NH4NH3, 5O2, 4NO, 6H2O. Okay, you are given the balanced equation and asked to find the enthalpy of the reaction. To calculate the heat of the reaction, or the enthalpy of the reaction, from standard enthalpies of formation, subtract the heats of formation from the reactants, multiply their stoichiometric coefficients from the heats of formation of their products, multiply their stoichiometric coefficients. So we find the heats of formation for the reactants and multiply it by their coefficient, and find the heats of formation of the products and multiply it by their coefficients. Okay, and that's what that formula means. So we're going to use that appendix. So here, NH3, its heat of formation is negative 45.9. But in our balanced equation, we have, where'd it go? There it is. Okay. Here's negative 45.9. But in our coefficient, in our balanced equation, it's the coefficient of 4. O2 is here, and it's 0, and so we're going to do 5 times 0. NO, nitrogen monoxide, is here. But the coefficient of the balanced equation is 4, and then water is here, and the coefficient of the balanced equation is 6. So basically, you just you look up their heats of formation, multiply them by their coefficients, and that's how you get the heat of formation of the reaction. Okay. So, a city of 100,000 people uses approximately use approximately 1 times 10 to the 11th kilojoules of energy per day. Suppose all of the energy comes from the combustion of octane to form gaseous water and gaseous carbon dioxide. Use standard enthalpies of formation to calculate the heat of the reaction for the combustion of octane, and then determine the number of kilograms of octane necessary to provide this amount of energy. So this plan has 3 parts. In the first part, we're going to write a balanced equation for the combustion of octane. Second part, we're going to calculate the heat of the reaction from the heat of formations of the reactants and products. But in the third part, we're going to convert kilojoules of energy to moles of octane using the conversion factor found in step 2. And then convert from moles of octane to mass of octane using the molar mass. So here's the solution. Okay, step 2. So we looked up our heats of formation for each of the following reactants. So we have, the first step, we have to write a balanced equation. So notice that C8H18 plus 25 over 2O2 gives us CO2 plus H2O. And then it says, begin writing balanced equation for the combustion of octane. For convenience, do not clear the 25 over 2 fraction in order to keep the coefficient of octane as 1. Okay, so we have to keep this as 1, because that's what we're looking at. And so we're going to keep the coefficient of oxygen as 25 over 2. So from then we use our heats of formation that we've looked up. And so the heat of the reaction, remember, the heat of the reaction equals the number of moles, the sum of the number of moles of the products, heat of formation of the products, and the sum of the number of moles of the reactants. So we have 8 heat of formation of CO2. Well, why CO2 on that side? It's because we have to flip this reaction. Okay, we have to flip this reaction because we are forming octane, or we're looking at octane. And so CO2 is on that side, water's on this side, and then we have octane and oxygen. So we plug in their heats of formation, and we subtract that out, and we get 5,074.1 kilojoules. From steps 1 and 2, build a conversion factor between moles and kilojoules. And then we're going to follow step 3 of the conceptual plan. Begin with negative 1 times 10 to the 11th kilojoules. Since the city uses this much energy and reaction must emit it, therefore there's a negative sign. Follow the steps to determine the kilograms of octane. So here we start with what we're given. This is how much the city's using. We know 1 mole of octane is negative 5,074.1 kilojoules. The reason we had to, back here, the reason we had to flip the reaction and, we didn't have to flip it because it's the products minus the reactants. But the reason that we had to keep octane as 1 is because this is how much is in 1 mole of octane. Or this is how much energy is in 1 mole of octane. And we need that in 1 mole so we can use it as a conversion factor. And then we have 114, and 1 mole of octane is 114.22 grams, and then grams to kilograms. That gives us 2.3 times 10 to the 6 kilograms of octane. That's a lot of octane. Okay, so I'm going to stop here. We may go over the energy use in the environment, but